All right, everybody, welcome back. Hope you had a good weekend. We're going to dive right in with one last example of imines in a biologically important reaction. And this is one that students tend to hate and they tend to worry about because it involves a molecule that's sort of large and complicated. But what we'll learn will be useful to you in biochemistry because nature actually uses this to transfer amino groups around. There are various reactions you will learn in biochemistry where you might think, why doesn't nature just use ammonia, NH3, to do that reaction? And the answer is that levels of ammonia in your blood can be toxic for various reasons, and so you need a non-toxic way of moving amino groups around, and nature will actually use imines to do this. And it will use imines using a molecule called PLP, which is actually one of the B vitamins called vitamin B6. And PLP stands for pyridoxal phosphate, and it's an aldehyde. So this is what it looks like. You've got a 6-membered ring containing nitrogen, and the ring is aromatic like benzene. The nitrogen has a positive formal charge on it. There's a methyl group here. There's an aldehyde here. And then over here is a CH2 group with an oxygen, and then there's a phosphoester on that oxygen. So that's PLP, or vitamin B6. Whenever I draw something like this, students naturally panic and they're like, do I have to have that memorized? I mean, yeah, if you want an A on the test, but no, come on guys. It's not funny yet, is it? Because you haven't taken one of my tests. Well, no, we're not really into memorizing structures. If you saw that in a lineup, it might be useful for you to pick it out as PLP. But the goal is not to memorize anything in exact detail. The goal is to look at a molecule like that and recognize the key functional groups. And for us in chapter 14, that's the aldehyde. Okay? So you should be immediately focusing in on the aldehyde, not so distracted by the rest of the molecule yet, but rather just focused in on that's an aldehyde, and I know that using an aldehyde and an amine, you can make an imine. So nature will take this aldehyde, and again, just focus in on there's the carbonyl carbon, and that's going to be our electrophile. And then one of the reactions that happens is for nature to take that aldehyde, that aldehyde, and react it with an amino group. So the amino group is often an amino group from an amino acid. So here is one of the amino acids. And the nitrogen that's going to act as the nucleophile is this one. Now, already you might be nervous about what we're going to do because we're simply going to do imine formation, but you can forget about a lot of the details because you already know how to deal with an amine that's a nucleophile that you could draw like this, and you already know how to deal with an aldehyde that's an electrophile that you could draw like this. So one of the goals of organic chemistry is to get you to the point where you can look at a complicated molecule and focus in on the parts that are most important. For us, that's the amino group and the aldehyde, and then temporarily in your mind at least abbreviate everything else. Okay? Now I'm not going to draw the mechanism for you for imine formation. It's several steps long. We went through it in detail last time, and I expect you to know how to do that. You don't have to draw out the mechanism with everything shown. You could abbreviate things like this, but you should definitely be able to show a reasonable mechanism for imine formation. But I'll go ahead and draw the imine that forms when PLP reacts with the nitrogen of an amino acid. Okay, here is still in blue what used to be the carbonyl carbon. There's the aldehyde hydrogen. In purple is the nitrogen that was from our amino group. And then we'll draw the rest of the molecule here. Okay, so that's the imine that we made from the aldehyde and the nitrogen. Questions about that? Do you see where that came from? Do you see how that's an imine functional group? Okay, so that part just applies what you learned last time. What happens next is kind of interesting because we're going to undergo tautomerization. Remember that tautomerization is simply changing where a pi bond is and changing where a proton is. The proton that's going to be involved in tautomerization is this one. The pi bond that's going to be involved in tautomerization is this one, the carbon-nitrogen pi bond. Because the goal of this reaction, I haven't told you where we're going, but the goal of this reaction is going to be to separate this nitrogen entirely from the amino acid. I told you that this was an aminotransferase reaction, that this is how biology moves amino groups around. So what's going to happen in this step? If you look at this hydrogen that I've outlined here, highlighted here, it is on a carbon that is alpha to this carboxylate group. It's adjacent to the carbon-oxygen pi bond, but on the other side, it's also adjacent to a carbon-nitrogen pi bond. You could imagine that if we removed that proton, the negative charge that would be left in its place would be resonance stabilized in two different directions, right? Resonance stabilized with the carbon-oxygen pi bond, resonance stabilized with the carbon-nitrogen pi bond. So it's sort of alpha to two carbonyls. So you'd expect that hydrogen to be more acidic than a standard sp3 hybridized carbon-hydrogen bond, and indeed it is. We can remove the hydrogen. Now I'm going to do what some of you who are taking notes with a pen and paper are going to hate. We need to save a little bit of time, so we're going to copy and paste, and I apologize for that. But you can go ahead and complain about it, and I will tell you, like I tell my children when they complain, I'm sorry, but I don't care enough to do anything about it. One of the great liberating phrases you can use as a parent. Write that one down. It will come in handy in about 15 years. Okay, so when that hydrogen is removed, the negative charge, I'm just going to continue to use orange to highlight stuff having to do with the negative charge, can be delocalized onto not only this carbonyl oxygen, but also by resonance onto the carbon that I just highlighted in orange, what used to be the carbonyl carbon in pyridoxal phosphate. Do you see how we could get that resonance structure? I'm going to just use arrows to draw that resonance structure, and we'll use, we'll use our double-headed resonance arrow to indicate this. Because I feel bad for you, I actually do care. I'm going to slow down and we'll actually draw the molecule again. All right, so we'll draw the resonance structure in which the negative charge from that orange alpha carbon is actually now on the pyridoxal, what used to be the pyridoxal carbonyl carbon. Do you see how this is a resonance structure of what's above? But if you're paying attention to what that resonance structure does, well, actually, let's pause there. Any questions about how to get to this resonance structure? Okay, so the negative charge is delocalized. If we now protonate on the orange carbon to the left, that's going to accomplish the tautomerization step. So we'll pick up a proton from some acid, probably an enzyme side chain. So the tautomerization involved losing a proton first, then getting to this resonance stabilized intermediate, and then gaining a proton. And once we gain that proton, let's draw what we have left over. Okay. Now I'm going to continue to use highlighting. Here was the nitrogen that originally we used as our nucleophile, and here is the carbon that was originally our carbonyl carbon. Notice that this intermediate here is tautomerized version of this intermediate here. Notice how they differ in the location of a carbon-hydrogen bond and in the location of a pi bond. Now, is this still an imine? Still matches the criteria, right? Still a nitrogen doubly bonded to an oxygen. Where's the carbonyl carbon now? On the left or the right? Used to be what was the original carbonyl carbon, which had 2 bonds to a heteroatom, now only has 1. Just by tautomerization. And what used to be an sp2 hybridized carbon here, sorry, let me say that again, what used to be an sp3 hybridized carbon here, prior to tautomerization, is now an sp2 hybridized carbon. Do you see how that tautomerization step switched where the carbonyl carbon was? Used to be on the left, now it's on the right. I'm getting some blank stares, so I need some feedback as to whether or not that's making sense, and if it's not, raise your hand, ask a question. Yes?
So do we still call it carbonyl carbon if it's double bonded to nitrogen?
Do we still call it the carbonyl carbon if it's a carbonyl carbon if it's doubly bonded to the nitrogen? Yes. So I'm worried about the color scheme. Maybe we need to make this one the blue one now, right? Yeah. So the effect of this reaction because of tautomerization is, well, you make the imine first, you tautomerize, and that switches which is the sp3 carbon and which is the carbonyl carbon. Yeah?
So from what we've learned so far, carbonyl carbons are always double bonded to oxygen, but is this a new thing?
So, yeah, the question is, we've always talked about carbonyl carbons as doubly bonded to an oxygen. I'm using that terminology for imines too, doubly bonded to a nitrogen, because you can get an imine from an aldehyde or a ketone. And once you have the imine, you can always hydrolyze and go back to the aldehyde or the ketone. So in my mind, I'm still calling that the carbonyl carbon because that's what it used to be and that's what it may yet be again. Yeah?
Are these in equilibrium, the tautomerized?
Yeah, in tautomerization are the two in equilibrium? Yes, you could go backwards as well. And nature will do this forwards and backwards depending on where it needs the nitrogen to be. Okay? So what's the point of all of this? Let's go ahead now and hydrolyze the imine. And this is good from a predict the product sense. If I'm going to hydrolyze the imine, I want to identify the nitrogen and the carbon that it's doubly bonded to. When I hydrolyze the imine, those are the two bonds that I'm going to break. Hydrolysis involves water coming in as a nucleophile to attack the carbonyl carbon. There will be some proton transfer steps. In the end, though, what's going to be left on the what's going to remain on the right-hand side of this molecule once the hydrolysis has occurred is there's the carbonyl carbon and there's the oxygen. Where does that oxygen come from? It comes from water. We're going to do hydrolysis. That's what hydrolysis means, right? We hydrolyze the imine. What's left on the other side? What's over here? Well, we're still going to have the 6-membered ring with double bonds in it. We're still going to have the phosphoester. But over here now, you have an sp3 carbon and a nitrogen. Okay, so your amino acid, what used to be your amino acid, is now an alpha keto acid. And what used to be an aldehyde is now a primary amine. That's why it's called an aminotransferase reaction, because the nitrogen was transferred from the amino acid to PLP. After the reaction, this is PLP is actually now called, and you don't need to memorize this, pyridoxamine. And this can now be trafficked and go to wherever it needs to be. And then nature might find another alpha keto acid and need to put an amine group in place of the carbonyl, and it can go backwards. That is, it can take pyridoxamine, form an imine with the alpha keto acid. That gets you here. Tautomerization does the switcheroo as to which side is the carbonyl carbon and which side's sp3. Then you hydrolyze that imine, and you've just made a new amino acid. This happens all the time in amino acid metabolism, and it's one of the ways your body moves nitrogens around. Okay, questions about that? Are you sure? Okay. All right, so we need to move on from imines. One thing, but we can't yet because there's one last thing we need to do, and that is, if you've noticed in all of our imine examples from today and last time, the amines are primary amines. That is, the nitrogen is attached to one and only one carbon. And if you remember last time from the imine formation mechanism, let's see if I can pull it up quickly. Once we get to, let's see, is that imine formation? Yep. Once we get to this stage where we've kicked off water as a leaving group, we get to the iminium ion. The fact that that nitrogen is bonded to one and only one carbon means that you can remove the proton from the iminium ion to get the neutral imine product. Okay? That's only, though, if you're using a primary amine. You could ask the question, what if our amine was bonded to two carbons? What if we used what's called a secondary amine? That's the abbreviation for secondary. So let's see how that might happen. Let's use an amine with two alkyl groups. And then let's use this ketone, and we'll use some acid catalyst. Now, I'm not going to show you the mechanism. You're going to need to review that. We're going to go all the way, we're going to skip all the way forward to the iminium ion. Just to say it in words, we would protonate the carbonyl oxygen at the same time as nitrogen is attacking. To get a tetrahedral intermediate, we would use a few steps of proton transfer to change who the good leaving group is. Then the nitrogen would kick off water as a leaving group, and we would get to the following iminium ion, which looks like this. Compare that to the iminium ion if we had used a primary amine. Then the iminium ion here would have looked like this. And at that stage, we can regenerate our acid simply by deprotonating the nitrogen. That's not an option here for the iminium ion that we get from the secondary amine, right? So what are we going to do to regenerate our acid catalyst? Well, our attention shifts to the alpha proton. For reasons we talked about a long time ago, meaning 5 or 6 lectures ago, protons that are alpha to carbonyls are somewhat acidic. more acidic than you would expect for an sp3 hybridized carbon-hydrogen bond. And the reason for that is, first, the conjugate base is resonance stabilized. That is the simplest explanation. Okay, and to show that, we would simply draw a base removing the proton. And we'll put the negative charge on the alpha carbon. But you will see very quickly that that negative charge is stabilized by resonance. You can draw a resonance structure where this charge moves over to form a pi bond, and then we break the carbon-nitrogen pi bond, and electrons move out onto what used to be the positively charged carbon, positively charged nitrogen, and we get this neutral resonance structure, okay? So, removing that alpha proton, you expect that alpha proton to be acidic because its conjugate base is resonance stabilized, as shown here. The second reason that alpha protons are acidic is that thing we talked about, hyperconjugation. Hyperconjugation between the filled sigma CH bonding orbital on the alpha carbon and the pi star, in this case the carbon-nitrogen pi star. We talked about that. We'll review that again, but those are the two explanations for why protons alpha to carbonyls are acidic. But if we remove, and in this case it should be, the conjugate base of our acid, removes that alpha proton, we regenerate our acid catalyst, and our product here is no longer an imine, it is called an enamine. Enamine, which is what, and the reason it's called an enamine is because you have the alkene, and then on the same, one of the two sp2 hybridized carbons, you've got an amino group. And most people spell it without that E there, but the E in enamine is a long E. You don't want to call it an enamine because either it sounds like you're talking about an enemy or you're talking about a medical procedure. So, enamine. All right, questions about that? How do you know when enamines form? It's just a secondary amine, right, with an aldehyde or a ketone. Now, you should be aware that just like imines can be hydrolyzed under acidic conditions when you supply water, so enamines can also revert back to the carbonyl carbon and the nitrogen. We do not have time to draw the enamine hydrolysis mechanism. There are sufficient details in your notes and in what I just showed you to be able to do it. You would start with the enamine, you would protonate on the alpha carbon with the acid to generate an iminium ion, and from that point on it would be exactly the same as imine hydrolysis, which we did go through last time. You should probably go through that, make sure you know how to do it, but it's not new and you already have the tools to be able to do it. Okay, questions there? All right, enough with nitrogen nucleophiles. Let's now talk about what if we used an even weaker nucleophile, water or alcohols, okay? We'll start with alcohols. With aldehydes and ketones as our electrophiles. Mechanistically, what's going to happen here is very similar to what happened with using amines or nitrogens as nucleophiles. The basic principle, though, is alcohols are weaker as nucleophiles than amines. You can tell that by comparing the pKa's of their conjugate acids. Because of that, alcohols will require what I told you was specific acid catalysis. That is, we protonate first, and then the nucleophile will attack the oxonium ion, which is the conjugate acid of a carbonyl compound. Recall the distinction with imines, we protonated while the nucleophile was attacking, but alcohols are less nucleophilic, they're not as reactive as amines, so they will wait for the carbonyl compound to be protonated first. So let's just show how that happens. We'll take a generic aldehyde and an alcohol, and the alcohol won't attack first. Instead, it will wait for the carbonyl compound to be protonated by the acid catalyst. That's an equilibrium step that generates this, what I will call an oxonium ion. Then, and only then, is the alcohol nucleophilic enough to attack the carbonyl carbon. That makes sense, or it should make sense, because you have a neutral alcohol, and when it attacks the carbonyl carbon of the oxonium ion, you can see that it generates a neutral OH group. Neutral alcohol should be totally reasonable to generate a neutral OH group in the tetrahedral intermediate. Okay? At that stage, it would be totally reasonable for this neutral oxygen, this neutral OH group, to be a kicker-offer that would kick off the alcohol nucleophile, right? That would just be the backwards step, and that happens. This is an equilibrium reaction. As with imine formation, you will see that we're gonna have to do something later on to push this reaction to completion. So, keep in your mind that the pink kicker-offer group could totally kick off this alcohol as a leaving group to go back to the oxonium ion. However, if instead the conjugate base of our acid deprotonates the purple group, the proton on that positively charged oxygen, that gets you to a neutral intermediate. Now, if you're thinking by analogy to and these R groups are different, they don't have to be the same, but I'm not going to worry about that in the way I've drawn it. If you're thinking by analogy to imine formation, at this stage we called the neutral intermediate in imine formation a carbanolamine. For what we're doing now using alcohols, we're going to call, as a nucleophile, we're going to call this a hemiacetal. That will make sense once I show you what an acetal is. Hemi means half, so this is halfway to an acetal. They didn't want to call it a half acetal because that sounded like something, I guess. Thank you. My oldest son has gotten to I've never tried that live, and I'm not sure is that a BYU appropriate dad joke? I don't know. My oldest son is taken to rating my dad jokes, so I'll get that was a 3 out of 10, Dad. I'm like, all dad jokes are about 3 out of 10. So I feel like mission's accomplished when he says that. Anyway, you will recognize the hemiacetal because it's got an OH group and an OR group on the same carbon, the one that used to be the carbonyl carbon. So that's going to be kind of important to keep you oriented. You can recognize a hemiacetal. It's got an OR group and an OH group on the same carbon that used to be the carbonyl carbon. Just as a hint, if you look at a hemiacetal, you can tell whether it came from an aldehyde or a ketone. The way you do this is you first identify the OH group and the OR group, then you see what else is connected to that blue carbon. If it's 2 R groups, used to be a ketone. If it's an R group and an H, it used to be an aldehyde. Does that make sense? Okay. So now, it turns out that in some cases, the hemiacetal is a stable molecule. In most cases, it is not. So I'm just going to write here, not generally stable, unless it's cyclic. And we'll get to exceptions. We'll get to what we mean by unless it's cyclic in a little bit. For a reaction where you're in equilibrium, if an intermediate isn't stable, that means it's not your final product. Because in an equilibrium, your final product is the most stable thing. So what happens at this stage is the acid gets involved again. If the acid protonated the purple oxygen, that would simply take us back to the previous step, and that happens. But the lone pairs on the pink oxygen are also available. And so we're going to draw what happens when the acid protonates the pink oxygen. All right. So now we've sort of, above I mentioned that the pink oxygen could kick off the purple leaving group. Now we've switched who the good leaving group is. Now the pink group has become a decent leaving group, and now the purple OR group has become the kicker offer. So what we will do now is the purple oxygen electrons kick down and water leaves. So far, we're exactly analogous to imine formation. If you're following along, it was at this stage of imine formation that we lost water as a leaving group. And if you want this reaction to progress to completion, you use Le Chatelier's principle to remove water. At this stage, what we have is a new oxonium ion. And here's our OR group that we used as a nucleophile. Now, unlike imine formation, there is no proton to be removed from that positively charged oxygen. You might ask, why don't we do what we did for secondary amines and enamines? That is, why don't we remove an alpha proton and get to an oxygen version of an enamine, something that might look like this? And I will tell you that what I just proposed, and imagining you're thinking about, exists, and it's called an enol ether, but it's not the major product here, for reasons we don't need to worry about. So instead of removing an alpha proton at this stage, what happens is a second equivalent of your alcohol, and now we need another shade of purple. I don't know, maybe we'll just continue with purple. Second equivalent of alcohol attacks the oxonium ion to give us another tetrahedral intermediate. Again, this should look reasonable to you because you're taking a neutral oxygen and it's attacking a carbonyl carbon, and you're making another neutral oxygen out of it. So here is the group that just attacked. Here is what was originally on the oxonium ion. At this stage, it would be totally reasonable for electrons on this oxygen to act as a kicker offer to kick off this as a leaving group. That would simply take us back to the previous step. But we can use the conjugate base of our acid to regenerate our acid catalyst by removing a proton from the positively charged group, and that's going to get us to this final product, which is our final product here. And this is the functional group that's called an acetal. Okay? You can recognize it as an acetal because it's got two OR groups attached to what used to be the carbonyl carbon. So what I've just shown you is acetal formation. That's kind of involved. It's about as long as the imine formation mechanism. But it's pretty important because it really tests, do you understand how to attack carbonyl carbons, and do you understand acid catalysis? One of the challenges when we have reactions that can go forwards and backwards is that students are not sure what to do at what stage. And the way to do that, the way to work your way through that is to practice it both forwards and backwards, always remembering where you want to end up. So if you're starting with the aldehyde and the alcohol, you protonate first, the alcohol attacks the oxonium ion, then you need to trade who's the good leaving group so you can eventually lose water as a leaving group. Then a second equivalent of alcohol comes in, you remove the proton, and that gets you to the acetal. Okay? One thing that you should do is practice acetal hydrolysis. That is, you can start with this acetal as a starting material, and you can use water, an excess of water, and some acid catalyst. And students sometimes struggle to predict what's going to happen here. Again, focus on identifying the key functional groups. In blue is what used to be the carbonyl carbon. In purple are the two OR groups. The product is the OR groups fall off as alcohols, and what you're left with is the aldehyde. Where does the oxygen on the aldehyde come from? It comes from the water that's going to attack the oxonium ion as a nucleophile. I'm going to leave it to you as a challenge to fill in the mechanism for acetal hydrolysis. Some of you would prefer if I held your hand and showed it to you, but you already have everything you need to do it. That is, you can copy this mechanism down, erase all the arrows, keep the intermediates exactly the same, and then see if you can connect the dots from acetal to starting materials. Okay, I want you to practice that. And if you promise not to look until after you've practiced it, I'll write down the answer later so you can check it in the notes. Deal? Okay. All right, so that's forming an acetal. Now, interestingly, the acetal is a second example of a protecting group. You can actually use the acetal to protect aldehydes and ketones so that they are not reactive. And the reason that this works is if we just consider the acetal, PG stands for protecting group, the acetal lacks acidic protons, but it also lacks the carbonyl oxygen. There's no pi star, so acetals are not electrophilic. That means acetals can survive basic and or nucleophilic conditions. Of course, they are, for protecting groups, we use this term labile. That means under what conditions would the group fall apart, and acetals are labile to aqueous acidic conditions. So let me show you an example where you might use an acetal as a protecting group. Suppose you have this molecule that has both a ketone and an ester in it. And, you know, esters and ketones are more reactive than esters, and yet both ketones and esters will react with organolithium reagents. Supposing you wanted to make the following product, and actually I want this to be an aldehyde, so hopefully you can live with that. Supposing you wanted to make the following product, this tertiary alcohol, and you wanted to leave the aldehyde intact. And you were going to do this with ethyl lithium, and you were hoping that you could deliver those 2 carbon units as nucleophiles to the ester. problem, of course, is that ketones and aldehydes are more reactive than esters. So what you would actually observe after this reaction was done is probably modification in both locations. That is, sure, you would get the tertiary alcohol from the ester, but then you would also deliver your nucleophile to the aldehyde carbon because the aldehyde is more reactive than the ester. So this is a situation where you would need a protecting group. So here's your strategy. The protection reaction might be to use an alcohol, which I'm just going to abbreviate as ROH, and then some acid catalyst, okay? And for fun, let's use our acid catalyst being one that you learned about in 351 that many of you have forgotten, and so when I write it down, you're going to be like, oh, I vaguely remember having heard about that, but I have no idea what it is. So here's your 351 review. TSOH is para-toluene sulfonic acid. It looks like this. It's simply an organic soluble acid. That's important because you don't want water present, because water under acidic conditions hydrolyzes acetals. Because ketones are more reactive than esters, you can modify the ketone without to make an acetal without messing with the ester. And by the way, that's no longer a ketone because I changed it. It's an aldehyde because aldehydes and ketones are more reactive than esters. So you would hope to be able to make this that's the protection reaction. Then you could add your organolithium reagent, which I guess we said was ethyl lithium. It can't react with the acetal. There is one and only one carbonyl carbon in this molecule. The acetal is not reactive to nucleophiles or bases. So indeed, you could get your desired tertiary alcohol, delivery of two of those organolithium reagents to the carbonyl carbon of the ester. At that point, you do the deprotection reaction, which is acetal hydrolysis. And again, that's simply adding water and a catalytic amount of a strong aqueous acid. That should liberate the aldehyde. I think I've kept the right number of carbons there. And then whatever these OR groups are, they will fall off. And you can generally isolate small, simple alcohols from more complicated products. All right. Questions about using acetals as protecting groups? Go ahead.
I understand the aldehydes are more reactive than esters, but why would the protection reaction not affect the ester at all?
You'll see later, the question is, why does the protection reaction not affect the ester at all? Could you use this acid to protonate the ester oxygen? Yes. You will see in chapter 16, we will do chemistry with esters in that way. Most of the time, we'll do ester hydrolysis, where we protonate the oxygen and then attack with water. It turns out that because the aldehyde is more reactive than the ester, you can protonate the aldehyde and have the alcohol attack the aldehyde before the ester gets involved. So it's not that you don't protonate the ester, it's just that the alcohol preferentially attacks the aldehyde carbon because it's just more electrophilic. Yeah?
Does the acid protonate at the same time as the alcohol attack?
We think the question is, does the acid protonate at the same time as the alcohol attacks? We think because alcohols are less nucleophilic than amines, that for alcohols you protonate first and then the attack happens. And that's called specific acid catalysis. That's different from what happens with amines, where it's general acid catalysis where you attack while you're protonating. Other questions? Okay, let's see. Little bit of fun, right? The whole class has been fun. What am I even talking about? Sometimes when you're when you're making protecting groups or when you're making acetals, sometimes instead of requiring two different equivalents of alcohols, do you remember the acetal mechanism where one alcohol attacks and then later the second alcohol attacks? Sometimes it's convenient to build in both alcohols into the same molecule. So here is an aldehyde. Actually, for fun, let's make it a ketone, and let's just make it acetone. And then we're going to use the following molecule as both alcohols. This is called ethylene glycol. It's like the major component of antifreeze. It's 2 carbons and then 2 oxygens. And then we'll use an acid catalyst. This reaction is going to involve making a 5-membered ring, and I know that when that happens, your brain tends to shut down. 5-membered and 6-membered rings are somewhat scary. I don't know if any of you have ever watched SpongeBob SquarePants. I wasn't really ever into it, but there's this famous scene where SpongeBob forgets somebody's name, and then we zoom into SpongeBob's head, and in his brain are a bunch of mini SpongeBobs that are running around rifling through filing cabinets, throwing papers, looking for what's the guy's name, and suddenly everything's on fire. And I know that's what happens to you when you're in the testing center and you see something like this and you have to make a ring. So our goal today is to tame your inner SpongeBobs that are in your brain and your filing cabinets that are on fire. We're going to skip ahead in the mechanism to the last oxonium ion. We're going to skip ahead to this state, and I will draw the intermediate that forms at that state. So water's already left, and you've got this oxonium ion. What can happen next is called intramolecular nucleophilic addition, an intramolecular reaction. That is, we don't have to wait for another alcohol that's on another molecule to come in and attack because we've got one here. And it turns out that intramolecular reactions that make 5 or 6-membered rings are generally pretty favorable in organic chemistry, in part because the oxygen, if you actually make a model, this oxygen is decently close to the carbonyl carbon. It's right there. So it's actually really fast for that oxygen to do the attacking. That generates this intermediate. Now, whenever you do something like this in an intramolecular reaction, simply just count the atoms that are involved, and that tells you what size ring to make. And then use that counting pattern to draw what the product should be. Then at this stage, we would use the acid to deprotonate, and that would get you to a product that is an acetal. You might not recognize it as an acetal unless you abbreviated it to look like this. But see, acetals don't care if their 2 R groups are actually linked to each other. That's just fine. So you need to get used to looking at something like that and saying that's just an acetal where the 2 OR groups are on the same molecule. And now with that, I'm gonna send you to go look for the Wikipedia article about nanoputations, because there's this whole field out there about 15 or 16 years ago. A research group at Rice University, I think, wanted to get kids excited about chemistry. And so they decided, realizing that this kind of acetal looked somewhat like a face, decided to make what they called anthropomorphic molecules, that is, molecules that look like stick figures. So with a little bit of creativity, you can come up with a lot of different head groups for various nanoputations, and there's nano chef, there's nano kid, there's nano scholar. Look it up, it's funny. All right, see you next time.